I'm Professor Rad, and this is Precalc video 2.8, Multiplicity and Power Functions. So now that we've achieved our goal of factoring a polynomial and being able to solve an equation, polynomial equals 0, we need a new goal, right? So our new goal is going to be graphing a polynomial function. So we know if we have a linear function, we can use the slope and the y-intercept and to graph the function. Or if we have a parabola, we can use the vertex and a point in the axis of symmetry to get us to graph the parabola. So now we need some new techniques for if I have a higher order polynomial. So like if I have like the x cubed function, we know it's got that little shimmy happening through the origin. So how do I know if a function is going to have a little shimmy? How do I know if it's going to have a turning point? All those sorts of things. So we're going to start out talking about multiplicity to figure out more information about whether we're going to be crossing the x-axis or whether we're going to have a turning point at the x-axis. And then we'll use power functions to help us determine like the end, the outside behavior of our function. So let's get started. So here's our definition for multiplicity. If you have x minus r to the m as a factor of your polynomial, and that m is the highest exponent it can be, so it has no other factors of x minus r, then the multiplicity is going to be m. Now, the multiplicity is going to help us determine what the function does at its x-intercept. So if the multiplicity is even, that means that f of x is going to touch the x-axis, meaning there's a turning point there. So think about x squared, just the basic squaring function. So if you have the x squared function, it touches the x-axis at the origin as it turns around. So if you have an even multiplicity, like squared, that's what's going to happen at that x-intercept. If you have an odd multiplicity, now it's going to cross the x-axis. So think about y equals x, so x to the first, an odd exponent, or y equals x cubed. Both of those functions go through the origin and pass through it. They cross the x-axis at that intercept. So if you have a root that has a multiplicity that's odd, you're going to cross the x-axis at that point. So let's do an example of identifying the roots or the x-intercepts of a function, determining the multiplicity, and identifying the behavior, whether it will touch or cross at that intercept. For this example, we're going to identify the roots and the multiplicity of each root and the behavior of the function at each root for this polynomial function here, 3x squared, x minus 4, x plus 3/10 quantity squared, and x plus 1 quantity cubed. Now, when you are going to determine the multiplicity of a root, you need to have your polynomial completely factored. So as factored as you can get it, so that we can make sure that there isn't, like, for example, another x plus 1 out here that could be kind of joined up with this one. Once you have that, to identify the roots, anywhere that you have a factor that involves an x, that's going to indicate a root. So for example, if I look at this factor here of x squared, that means that we're going to have a root of 0. If you want to think of it like x minus 0 quantity squared, you could. So this is where we're getting that r value of 0. That just means in this case, the polynomial function will be going through the origin. Now, I'll also point out this 3 here. This 3 is just a stretching factor of this polynomial. So it doesn't impact the roots in any way. So if you don't have an x all by itself, or like an x squared or x cubed, then you won't have a root of 0. Because the exponent on the x, or on this factor, is a 2, that means our multiplicity is going to be 2. And because 2 is an even number, that means the behavior at this intercept of our function is going to be to touch the x-axis. That means we're going to have a turning point there. And we're going to repeat this process for each of our roots. So the next one is x plus or x minus 4, I'm sorry. So that means 4 is going to be our root. Now there's no exponent written on this factor, so that means it has an implied exponent of 1. So this has multiplicity 1. And because 1 is an odd number, that means its behavior is going to be to cross the x-axis. All right, if you'd like to pause the video here and try the next two on your own, see if you've got the, the swing of it, feel free to do that. And then you can unpause and we'll go through it and check. So for this next factor, we have plus a 3/10. So that means our intercept is going to be at negative 3/10. We have a power of 2 here, so the multiplicity is 2. And because that's even, that means we're going to touch or turn around at the x-intercept. And lastly, for this factor, we have x plus 1. So that means r is going to be negative 1 because our factors are set up as x minus r, so we change our sign. The exponent here is a 3. And because 3 is odd, that means we're going to cross at the x-intercept. So that's it for our multiplicity. So what multiplicity helps us to do is it helps us to understand the behavior of our polynomial function kind of on the inside. So kind of close on the inside of our graphing space so we can see what's happening. We also are going to need to know what happens on the ends. So if you think about your cubing function, the cubing function goes down on one side and up on the other. So it's kind of like, wee. Whereas your parabola goes up on both sides, or if it's a negative frowny parabola, it'll go down on both sides. So how can we predict what's going to happen to the extreme end values of a polynomial? Well, the good news is, as long as we can identify the leading term, we can identify the extreme, like the end behavior. So let's check out that theorem. So here's theorem 10. So this theorem states that for large values of x, a polynomial function is going to behave like its leading term. So this is why when we were identifying different features of a polynomial, the leading term and the leading coefficient and the degree, all those components were important because they're going to help us identify the behavior if I have like a big long string of x's, right, in my polynomial. So it turns out the factors and their multiplicity are going to help us zero in on the middle behavior of our function, while the leading term is going to help us understand that end behavior. So remember, if you have a polynomial that only has one term, we call that a power function. And so if I have just the leading term, that's going to be a power function. So if we understand power functions, then we can understand all polynomials. So let's take a moment and break down some of the pieces or some of the components of power functions. All right, so before we begin looking at the different properties of our power functions, let's just take a moment to look at some basic power functions. And let's use this graphing software to help us figure that out. So first, I'm going to graph a bunch of power functions that have an odd degree. So we should all know what the line y equals x is going to look like. And you'll notice that my x-axis here is a little bit more narrow than my y-axis. That's totally fine. So if I have the function y equals x, we can see that it's going to go off towards negative infinity on the left and positive infinity towards the right. So we have our function going down as we move to the left and up as we move to the right. If I look at the next odd power function, so x cubed, this function, although it has a little shimmy in the middle, it does pretty much the same thing. So this function is going down towards negative infinity on the left, and it's going up towards positive infinity on the right. So the directional behavior is going to be the same for these two functions. In fact, this will be the case for all odd power functions. So if I look at x to the 5th, it does the same thing. It's just a little bit more narrow than the cubing function. And if I look at x to the 7th, same game. It goes up on the right and down on the left. Now, if we were to negate any of these, that would flip the functions over the x-axis, so the end behavior would be the opposite. So if I were to look at a negative x, so let's change this x into negative x, we can see now that it's going up on the left instead of down, and it's going down on the right instead of up. And the same thing would be true for any of these. So we can see that the end behavior for odd valued functions or odd power functions, sorry, is going to be that they go in opposite directions. If the leading coefficient is a positive number, that means it's going to go up on the right and down on the left. If the leading coefficient is a negative number, then we have the reverse. It's going to go up on the left and down on the right. So now that we've looked at some of our odd power functions, what happens if we look at even power functions? So we know our friend x squared looks like this, happy parabola here. If I look at x to the fourth, it's doing something very similar. The difference is instead of being as wide as a parabola, it's a little bit more narrow and it kind of squares out here at the base. And this will be the case for all even power functions. So if I look at x to the sixth, it's doing a similar thing. It's going up on both ends. And if I look at x to the eighth, we have the same thing happening. So as our exponent increases, notice that this is going to flatten out more at the bottom, but the end behavior is going to be the same. In this case, it's going up on both the left and the right. Or f of x is going to positive infinity as x goes to plus or minus infinity. And these all have a positive coefficient. If I had a negative coefficient, it would reflect it over the x-axis. And so it would be going down on both sides. So for example, if I have negative x to the eighth, now we can see it's going down on both sides. So now that we've had a chance to explore these graphically a little bit, let's summarize this information in a nice handy reference chart. Let's summarize our findings or observations from the graphs in this table here. So if you'd like to copy this down in your notebook, that's fine. I will point out that for both of these range values, I needed 3 lines in my notebook, and I needed 1 line for all the others. Okay, so now that you've got those copied down, let's go through and talk about the features of the odd functions, and then we'll talk about the features of the even functions. So, not surprisingly at all, if we have an odd power function, it's going to be an odd function. Pretty sure that's where they got the terminology from. So, an odd function, you'll remember, is symmetric through the origin. So then, our domain of our power function, you can raise any number to an odd exponent. So our domain is all reals. Or if you prefer your interval, negative infinity to positive infinity. Now, for the range of this function, if your leading coefficient or if your coefficient of your power function is positive, that means we're going to have a function that goes up on the right and it goes down towards the left. And goes up and down forever. So that means our range is also going to be all real numbers, or negative infinity to positive infinity. But let's make sure we specify that information about what's happening in either direction. So we can say f of x goes to negative infinity as x goes to negative infinity. So this is indicating that as I move to the left, x goes to negative infinity, my function is going downwards. Similarly, we can have f of x goes to positive infinity as x goes to positive infinity. So as I move to the right, the odd power function is going to go up. If my coefficient is negative, if it's less than 0, our range is the same, but the end behavior is reversed. So our range is still all real numbers, or negative infinity to positive infinity. But this time, f of x is going to go to positive infinity as x goes to negative infinity. So as I move left, the y values are going to go upwards, and f of x is going to go to negative infinity as x goes to positive infinity. So as I move to the right, the y values are going to decrease. So when I think of an odd power function, I like to think about the most basic odd power function there is to help me understand this end behavior. I find that very helpful. So what I try to picture when I have an odd power function is y equals x. Right? I'm pretty familiar with that common function, so I know how it's going to behave. I can kind of, if I had like negative 3x, I know a negative slope goes downhill. So I know about this information. And if I have a line that's got a positive slope, then I can go positive slope. I know how it's going to behave. So actually, I'm going to just go back in here and say y equals ax, because that coefficient is going to be important. It'll tell us whether the line goes up or down. So it'll tell us whether the odd power function goes up or down. So now let's repeat this analysis for our even power functions. So if we have an even power function, not surprisingly, it's going to have the even property. So odd power functions are odd, even power functions are even. That means for our symmetry, we're going to have symmetry over the y-axis. So we're symmetric about the y-axis if we're an even power function. For the domain of an even function is the same as the domain of an odd function, odd power function, because you can still raise any number to an even power. So our domain is still all real numbers, or negative infinity to positive infinity. And what's different now is going to be information about the range. So as we saw with like the squaring function, if you have x squared, it's going to be a parabola that's opening upwards. So its range is not all real numbers. It has a minimum of 0, and then it goes up to infinity on both sides. So if you have a positive coefficient, that means your range is going to start at 0 and then go up to positive infinity. In other words, f of x is going to go to infinity as x goes to negative infinity. And also, f of x is going to go to infinity as x goes to positive infinity. Whether I move towards the left or the right, an even power function is going to go in the same direction. Then if my coefficient is a negative number, now we're upside down, we're frowny parabola. So instead of going from 0 to positive infinity, if I flip that, I'm going to go from negative infinity up to 0. So my range is going to be from negative infinity to 0. And now it's going to go downwards on both sides. So f of x is going to go to negative infinity as x goes to negative infinity. So as I move left, the function goes downward. And it will also go downward, so towards negative infinity, as I move to the right. So as x goes to positive infinity. So to help me picture even power functions, what's happening on the ends, I'm going to think of y equals ax squared, most basic even power function that I can think of. All right, so now that we've kind of discussed some properties of power functions, let's put this to use and use it to help us determine the end behavior of polynomials. This next example is a fill-in-the-blank style example. So you may wish to pause the video here and write all of this out so you can fill in the blanks in your notes. So let's use those properties of power functions to help us fill in the blanks, to understand the end behavior of these polynomials. So the function f of x equals negative 2x to the 8th plus x cubed minus 7 will behave like a power function. To find the power function, we have to figure out the leading term. So because this is written for us in standard form, the leading term is pretty easy to find. So this function is going to behave like the power function negative 2x to the 8th. Now, what I like to do once I identify the leading term is to try and picture either x squared or x, depending on which one I've got. So in this case, because I have an even exponent, I'm going to be thinking of something like x squared. And because the leading coefficient is negative, I'm going to be thinking of a frowny parabola. So my mental picture that I have going on is this. That's going to help me identify the end behavior. So we're going to behave like negative 2x to the 8th for large values of positive and negative x. This means that f of x is going to go down on the left. So we could have downward or down on the left, and it's going down on the right. So there you go. That's how you can figure out the end behavior based on the exponent. Let's do another example, and this one's going to be a little bit trickier, of course, right? So this time we have a function g of x, and this time g has been given to us in factored form. But this is no problem. Way back in video 2.1, we talked about if you have a polynomial in factored form, how can you find the leading term? So the coefficient is going to be, in this case, 5 times 1 times 3. Neither of these factors have an exponent on them, which is nice. So we have 5 times 1 times 3 is 15. And then to get the power of x, we're going to add the powers of x's here. So we have x squared times x. So that'll give me an x cubed. Just as a refresher to figure this out, you could pretend like this -1 and this +11 weren't here. Again, because polynomials behave like their power functions for large values. So that's why we can discount these values here when we're trying to think about extreme values. So for large values of positive and negative x, this function is going to look like 15x cubed. Because this is an odd exponent, I'm going to think of my linear function y equals x, or more particularly 15x, right? Since that's a positive coefficient, that means we're going to be looking like we're going up on the right and down on the left. Now, this does not incorporate the little shimmy because that's what's happening in the middle of the function. Really, what I'm interested in is what's happening on the ends. So now we have a different notation. Instead of stating the direction of up or down, we need to state whether it goes towards positive infinity or negative infinity. So as x goes to negative infinity, as we move to the left, this function is also going towards negative infinity. Then as as x goes to positive infinity, our function is also going to go to positive infinity. All right, so in this video, we've discussed what's going to happen at the x-intercepts by using the multiplicity of our factors. And we've discussed what's going to happen for extreme values of x based off of the leading term, based off of power functions. So in the next video, now we're going to figure out what happens between those pieces. So what happens between the x-intercepts and what happens between the x-intercepts and the end of the function. So we'll look at turning points of a polynomial, and we'll look at another theorem called the intermediate value theorem. So I hope you found this video helpful in learning about multiplicity and properties of power functions. I'm looking forward to seeing you in the next one, but in the meantime, have a wonderful day. Bye for now.